So welcome back, everyone. Let's get started. So we'll be doing the third part of the linear algebra review today. So if you look at the schedule, so if you didn't see homework, so 2 is posted. So we talked a little bit about that. So last week on Thursday, 2 of the questions are from the convergence part of the prior 2 lectures, and then 2 of them are going to be on the linear algebra. So you should be able to do most of it after today. There's a question on Canvas, how to interpret something in the homework that we're going to cover today. So if you've looked at it and you don't know how to do all of it yet, so that should be okay. We'll cover more of it today. And then some of it will be covered on Thursday. So there are a few things about like having to do with mostly with square matrices that we won't finish today, that may also be on the homework. But my guess is you can probably look ahead and do most of the homework, almost all of it after today. So it's not due until, let's see, next week, so Tuesday, but you've time to get started. Again, the office hours will get very crowded on the couple days right before homework is due. So if you think you might want to get help from office hours, it might be better not to wait until the last minute. The other thing you'll notice is quiz number 2 is going to be on Thursday. Quiz number 2 will cover everything in the 2 convergence lectures that were the part of the book in chapter 2 that we covered, and also the first 2 lectures on linear algebra. I won't put anything on from the lecture on Thursday. So this will be my general kind of strategy with the quizzes. It'll be the previous 4 lectures is what the quiz will cover. And it won't necessarily, and it'll try not to cover the stuff that I'm lecturing about that day. Occasionally on the day of the quiz, we'll review a little something that will show up on the quiz. So it's, still good to come to that lecture before taking the quiz. But if you want to study for it and prepare it with like a cheat sheet, the core material will be the previous 4 lectures. So for most of the semester, this works out pretty well in terms of topics. This one piece of linear algebra might get covered in the next quiz, or it might not get covered in the next quiz either. But it should be covered in the first homework, and this is important topics. You'll need to, if you don't understand the stuff on the lecture on Thursday, it'll be harder to understand the properties in linear regression and dimensionality reduction and some other aspects of the course. So also today we'll be going through some examples in code using Colab again. What we'll mainly be going through is how to use the Numpy library. This is a library within Python that handles like the linear algebra stuff, the vectors and matrices and operations on them. So this library is great if you're doing data analysis. This is like your core kind of data structure will be within stuff within NumPy. So prior to NumPy, basically the only easy way of doing this was within MATLAB. If you've used so MATLAB before, the notation is similar, but so not quite the same. They're so some differences. When I was so in undergrad and going to graduate school, this was not really well developed. And I remember trying to code all this stuff like in C, and it was, you know, a big pain to deal with this stuff in C. It uses the same backend libraries to do the big kind of sort of calculation, but the interface here is much nicer, much easier to use. So again, I'll just show you examples, and then you'll be able to kind of replicate this stuff in the homework. Okay, so let's get started on the lecture. We're talking today about so norms, linear independence, and rank. So we talked before about linear algebra, algebra as so kind of being the way we're going to think about it is like the study of vectors and matrices. Okay, and I'll typically use lowercase letters, U, V, and like A, like as an AI, as like as vectors, and for matrices I'll use like uppercase letters, A and B. Typically, if these are these will often be matrices in R n by D, where these might be, say, d-dimensional vectors, right? So I write them as R as D, real values. So U might be U1, U2 up to UD, right? So this is an ordered set of U values. We'll almost always think about real values. Occasionally you'll think about like binary values or something as these vectors and matrices within this course, but we'll mostly be thinking about like real values. Like, of course, on a computer, these will be represented as like floats or doubles. And so it's going to assume we have like full precision here. There are a couple cases we'll start talking about, like some issues with precision. Sometimes you don't get things exactly like you would expect them to be, and we'll have to sometimes interpret, oh, this number, it looks like a really small number, but it's, you know, it's actually supposed to be 0 exactly. And so we'll have to use our knowledge of the mathematics underlying this to kind of interpret some issues with some rounding errors. But in most cases with data analysis, you often don't need to do that. If there's a rounding error that becomes an issue, your algorithm is probably not very robust with respect to the noise in the data. So most times it's fine to use just like floats and doubles, and often these are big computational issues. They'll use a float instead of a double. It has enough precision inside of a float. So matrices often A and B. These would be a square matrix, right? So it's going to have n rows. This would be the number of rows would be n, and the number of columns would be d. And then later we'll talk about some square matrices. These might be d by d instead. So where it's the same number of rows and columns. But this will mostly, we'll talk about on Thursday. What I want to talk today about first is something called a norm. Okay. And so this is a measure of scale of these vectors and matrices. So we had drawn pictures before where we thought of like a vector, say a vector v as being a point, right? So this would be in R2. So this might have a two-dimensional point v1, v2. Remember, v1 is this length here, and V2. So V2 is so it'd be the distance from the origin in the y-axis. What we're going to talk about now is the length of the vector, where we think about it as the difference between the vector as the point, and so the origin. We want to think about how large is this vector, and the norm is a way of quantifying this. So when we talk about the length, we'll think about the, so I'll write this as two parallel bars, V, and then two of these parallel bars. If you're just writing it like on the quiz or something, you can just write that there's actually a symbol on your keyboard that can do this. In LaTeX, you might do slash, then the parallel bar, and it'll format it slightly differently inside of LaTeX. Okay, so we want to talk about the length of this vector, and kind of, what we mean by the length is going to be in most cases, the Euclidean distance, okay? And so just the Euclidean distance of this vector V, right, is going to be V1 squared plus V2 squared, the square root. Okay, so this is the length of this vector. If I were to have a piece of string from the origin up to this point V, and I were to measure the length of the pieces of the string, then so this calculation would give me that value of that length. Okay. So this is what we will, in this course, basically what we will mean for the norm of, so a vector. I'm going to say a little bit more about generalizing this, and then we'll talk about norms of matrices, which are going to be, slightly more complicated. So in general, so we can talk about something called a P norm, okay? And so this will be written as, and this is for a vector in RD, and I'll write this more generally. So a vector, a P norm, so I'll write a subscript of the norm with the value P. P is going to be a value between 1 and up to infinity, and then we'll have a special case for infinity. Okay, and this will be equal to the sum of j equals 1 up to d of all of the coordinates vj, so the jth coordinate of the vector, the absolute value of this taken to the pth power. Okay? And then I'm going to take this whole quantity, I'm going to take the pth root of this whole, this whole quantity. Okay, so this is known as the P norm of the vector. So what's important here is I'm raising to the power P, and then I'm taking again to the power 1 over P. This means that, the way I'm measuring, the units, stays the same. So if every element of the, the vector, is like in, meters, right? Then the quantity inside of here, this would be like the unit to the power P, right? So if P was 2, it'd be like square meters, but then I take 1 over P, and that brings it back to meters again. So it's measuring length in the same sort of units as the original things in the vector. Okay, so that's why it's important to, if you have a P, if you raise to the pth power, you take it back down to the 1 over pth power, and so the units are staying the same, right? So then this quantity here, this is just, unit to the power P to the power 1 over P is just the same, units, so that it's going to keep so units I start with. So this is the pth power. This is a general version. If I wanted to recover the version I wrote on the the previous slide, right? So I have to choose a value of p. As it dawned on you what value of p gave me the result from the previous slide. 2. Yeah. So kind of the standard way of doing this is that V2, I'm just going to write this as just the norm of V, right? So if I don't write a subscript on the norm, it's going to imply the 2 norm, right? So this is the Euclidean distance. This is like as the crow flies, this is like measuring the distance of the straight line. And so in some cases, we won't write the subscript and it's, just going to mean the 2 norm, but you should know that there are more general norms. There is one I'll just mention. Another common one is the 1 norm, right? And this is equal to, I'll just write this out so it's clear, and then I'll simplify this. Vj absolute value to the power 1, and then 1 over 1, right? So the 1 over 1 is 1. Taking something to the 1 power does not do anything. So this is just the sum of Vj. So like the absolute values. Okay, so if I draw an example here, let's see, this is the origin, okay? And I have a point that is, say, here. So let's say this is V equals 4, so minus 2, right? So on the grid there, it goes, the x coordinate, it goes over length of 4, and then it goes down 2, right? So the L1 distance goes 4, you can think of it going 4 along the x-axis and then down 2, and it's the length of the blue line instead of the straight line, right? So this is still a notion of length. I could have measured it in the other direction instead. I could have gone down first and then over, and so this would give the same distance. Note the absolute value is needed here because the minus 2 is still a distance away, so from the origin. So it didn't matter if it moved up or down, that's still increasing the distance. So I wanted the absolute value. In the case with the 2 norm, I didn't need to write the absolute value because squaring something always takes the absolute value of it, so sort of implicitly. There's also an important special case where, we still write this as the norm, where we write p is equal to infinity. Notice I claim that the norms were defined in this way for p between 1 and up to infinity, but not at infinity. And so this is what happens when I take p all the way to, as I approach infinity, this is what it converges to. And that's taking everything to a really large power and then taking that powerth root of it. And what that's doing is amplifying the largest things. Everything else becomes much smaller compared to whatever is the largest. And so in the limit, this is just equal to max of j equals 1 up to d of vj, of the absolute value of vj. So it's just the largest coordinate here. Okay, so in this case, if I look at v here and I take the L infinity norm, this is just equal to 4. The x coordinate is 4, the y coordinate is minus 2. 4 is bigger than 2, so that's going to be my norm here, okay? So there are other ways to model norms. The 2 norm will be mathematically nice. It measures the straight line distance. It shows up in a lot of algorithms. We'll see in some algorithms, it's nice to work with the 2 norm. So that's mostly why we'll use it in this class. If you go to more advanced classes, you will see uses of other norms, and so they're important. If you read further along in the book, more than what we cover in this course, you'll see places where these other norms are so going to be important. One of those is that some of this choice of how we measure kind of a length of something is like a modeling choice, where we're going to work with the 2 norm and a lot of algorithms in this class because they are easy to work with. They're simple algorithms, they're easy to understand, but we could make other choices and you get slightly different kind of sort of answers to things. And that's something to keep in mind within, so like the realm of data science. There's a lot of modeling that goes in that you as the data scientist can make that choice. One other thing, this actually gives a notion of a distance between high dimensional points. Okay, so let's say I've got 2 points, P and Q, and these are both points in RD, right? So these are both vectors, all right? And I can write that the distance between P and Q. So I want to say that if P and Q are close to each other, that this distance is small. If they're far from each other, this distance is so going to be large, right? So I can think of a picture here. I've got kind of P here, and so Q over here, and I want to know how far apart are these? Well, then the standard way to measure a distance is just the norm of P, so minus Q, right? P minus Q is going to be the vector from Q to P, and I want measuring the length of that vector, that black vector here. So this vector is P minus Q. I can think of that as a vector, so I do the subtraction first, and then I take the norm, and that tells me this, length. Okay, so this is useful in measuring the distance between objects. Any norm is a valid way of measuring the distance. If I were to measure the L1 distance, it would be the distance of the red line instead of the black, right? It's still a notion of a distance. Well, I won't say too much more about that. Also, I want to point out that there's a way to interpret the 2 norm as the dot product. Okay, so the 2 norm. To remember, let's write the squared 2 norm. So if I write a superscript 2, this is going to be squaring it. I put the parentheses around the outside here, so maybe it's a little easier to see. Maybe let me rewrite this a little bit more clearly. So often you don't write these parentheses, but so if I take P, I take the 2 norm, I just want to make this explicit here, and then I square it, right? So remember what this is, J equals 1 to D, that's PJ squared, right? Or the absolute value squared, but we can drop the absolute values. And then there was a square root, but I'm squaring the left-hand side. So I'm just kind of simplifying this by not dropping the square root. Okay, this is equal to the dot product between P and P. So itself, right? If I remember what the dot product was, so just remember my favorite operation, a way of multiplying 2 vectors with each other, gives you a scalar. J equals 1 to D is Pj times Pj, right? So it's times itself, that's just squaring itself, right? So I'm taking the dot product of P with itself, and I take all the pairs of matching coordinates, I multiply them together, and I add those up. That's the same thing as the squared norm, right? So the dot product is, again, capturing the length or the squared length of the vector if I take it with itself. Okay, so this will be a useful property to have later on in the class. All right. Okay, so these are kind of vector norms, what you need to know. You'll calculate some of these on the homework and maybe on the quiz. So it's good to know what they are. Again, the quiz, I won't make you do any really complicated calculations, but nothing you should need to use a calculator for, but you should be able to kind of understand what the, what the procedure is. So there's also, so matrix norms, okay, and these are kind of norms in the sense they're giving a sense of magnitude of some matrices, and there's, like with vectors, there are a variety of ways taking norms of some matrices. We're gonna stick with the versions that generalize the 2 norm, okay? But there are 2 ways to generalize the 2 norm of some matrices. There are ones beyond that I won't, beyond this that I won't talk about. But there are 2 ways to generalize the 2 norm. Okay, so if I have a matrix, and this is, again, this is an element of R n by D, right? So n by D, so matrix, right? Then there are 2 types of norms. The easiest one is the Frobenius norm, and this is written as A norm, and the subscript is going to be in uppercase F. Okay, and this will kind of essentially treat the matrix as if it was actually an n times d dimensional vector, and then it's going to take the 2 norm. Okay, so I'm just going to sum over all rows. Let's see, all rows and all columns, and I get an element Aij. And take this element, I'm going to square it. So I'm adding up all the elements squared, and then I take the square root. Okay. So if I were to take a vector, so if I were to take a matrix, and I were to go and to treat it as like this long vector, right? So I'm kind of going along one row, then I jump to the next row, and I string it out as an n times d dimensional vector. Then that would be the 2 norm of the vector. This is what the Frobenius norm is. So I could view that it's the same thing as if I took the columns and strung those together. It's going to give me the same answer. You can also view this. Another way of viewing this is I can say I equals 1 to n of the 2 norm squared of each of these. I'll put a 2 down here just to be clear, of each of the rows, right? So if this is A1, A2 up to AN, right? And I took the norm of each of those rows, and I took the squared norm, and I added up the squared norms, and then I took a square root at the end. That's the same thing as the Frobenius norm, right? Often working with the squared quantities is going to be easier. The same way we work kind of with variance a lot of times in the probability. It's easier to think about the squared quantities, and then you slap a squared root on it at the end to get back to something in the same units. The same way we did with standard deviations to the variance, right? So this is a notion of the scale of a matrix. As the values in the matrix increase, the value of the norm is increasing, or as they're deviating from 0, as they're getting further from 0 values, the norm of the matrix is going to increase. All right. Okay. So this is kind of a pretty straightforward extension. The other sort of matrix norm is the spectral norm. Okay. Spectral refers to things like like the eigendecomposition. We will talk about, in this case, we're going to have not necessarily a square matrix, so we can't talk about the eigendecomposition, but we'll talk about something called the singular value decomposition, which if you've heard of eigendecompositions, it's related to that. And the spectral norm refers to, it's capturing some property of that, okay? Where I'm going to define it now without talking about eigenvalues and such, and we'll see that version of this definition later in the semester, but that's where this name is coming from. And we'll write this as with a 2 in front here, with a 2 of the subscript. So if I have a matrix, a capital letter, take a norm and a subscript 2, this is referring to the spectral norm, okay? And you would think the Frobenius norm, you know, might be what you would put the 2 for, but this is the most common way of, you know, writing the notation for these things. And this definition, without using eigenvalue sort of language, is a little bit less intuitive, but it's written as max of x in Rd such that x is not equal to, so the all zeros vector. Okay, so I can't have the all zeros vector, and then it's the norm, the spectral norm, so the 2 norm of a times x divided by, so x. So by the 2 norm of x here. Okay. So this is a little bit trickier to think about. This is what's called, so called like a type of, so an operator norm. And I'm thinking about some operation. In this case, I'm multiplying by x and I'm taking the 2 norm in the vector space because a times x is then a vector. So then I'm taking the norm of this and comparing to this, and I'm maximizing over this operator. This is called, you know, like an operator norm, and this is how we're going to find it. So for now, you have a question? Oh, okay, great. So this is going to be equal. There's another way of writing this. I can also write this as max of y in Rn, where y is not equal to 0, where y times a, I think I need y transpose, depending on if you worry about the transpose or not. This is equivalent. I can also multiply it by, so the other side, then I need y is going to be an n-dimensional vector instead of a d-dimensional vector. You know, so it's not going to matter so much. And I can say, okay, the maximum vector multiplying by a vector on the left-hand side. Turns out this is going to give the same answer. Okay. Okay, so just a little quick properties you should see now. And we'll see why this is true later when we talk about the singular value decomposition and the interpretation of these here. But so the Frobenius norm is always going to be greater or equal to the spectral norm. Okay, so this one's always a larger quantity. This is kind of reducing it to a one-dimensional, the largest one-dimensional kind of view of this, because I'm reducing it to a vector view, where this is taking all the dimensions into account. For now, that's all I'm going to say about it. We'll get more intuition when we talk about the singular value decomposition in terms of like dimensionality reduction. Okay. Maybe I'll do just kind of a simple example. Let's say V is equal to a vector. Oh yeah, we did an example with vectors. We'll do some examples in Python as well. But so let's say I have a matrix that is equal to 3 minus 7, 2, minus 1, 2, so minus 5. If I were to calculate the Frobenius norm, let's just do the squared Frobenius norm of this. It's going to be equal to 9, that's 3 squared, plus 49, that's negative 7 squared, plus 4, that's 2 squared, plus 1 squared, negative 1 squared, plus 4, that's 2 squared, plus 25. Okay, and my notes say that this is 10.95 squared. So I don't have it written down. That's probably because I've only written down the full Frobenius norm. Let's see, that's probably 58 or 50 plus what? Well, it's the square root. It's not exactly 10.95. Let's see. That's the number I'd written down my notes for the non-squared version. Okay, I should now I've kind of left you hanging a little bit here. 50 plus 60 plus 12, 72. Right. If you take the square root of 72, you should probably get about 10.95. No? Okay. Well, I did. Oh, plus 25. I'm off. So 92. Still should be over 100. Okay. All right. Well, the 10.95 is probably incorrect. 9.5. Okay. 9.59 squared. Yeah. So that seems okay. So yeah. So let's write that down. But okay. So I won't actually ask you to do calculations this kind of challenging on the quiz, because I don't simply make mistakes. But if you're to ask to write down the Frobenius norm, you should be able to at least write something down that looks like this. Okay, and you can leave the calculations because it's easy to make mistakes there. You should be able to do this inside Python, and Python to make calculations for you should be a lot easier. So, all right. Okay, we will probably see what it is when we go to Python a little bit later. Yeah. Yeah, so I wrote in particular, I wrote the 2 here so that I didn't have to take a square root. And then I decided I wanted to take a square root anyways. So, it would imply that the Frobenius norm of F would be about 9.59, right? Because this is equal to the square root of a F squared. Okay, great. Yeah, good. Okay, yeah, this stuff's actually, if you haven't seen before, you're throwing these subscripts in there and then superscripts show up. Those usually mean squared. Usually we write them to avoid the square root or to not think about it or to save that computation for later, right? The square root is a much more expensive computation than just adding and multiplying. It's the way it's implemented in hardware. So you'd like to avoid taking square roots. Okay, great. So let's move on to linear independence. Okay. So this is a really important concept, and this is probably the trickiest thing we will talk about in the linear algebra review section. It's kind of a, you can think of it as kind of akin to the independence we've talked about with random variables, but this is kind of a linear algebra way of thinking about things are one thing does not affect the other part. Okay. And we're going to think now about having k vectors, x1, x2, xk, and these will be in vectors in RD. So they're all of the same length. We'll be thinking all vectors of the same length. We're also going to have k scalars, alpha 1, alpha 2 up to alpha k, and these will just be values. These will just be real values. And then, one of the kind of cool things about linear algebra is I want to think about the vector I get as, let's use I here, by adding these things up. Okay, so what am I doing here? I'm multiplying each vector by a scalar. Here, this should be alpha I, right? So each vector by its own scalar, so that's scaling it, making the vector longer or shorter, and so forth. And then I'm adding up these vectors, and the result again is going to be another vector z, rd, which is also going to be in like a d-dimensional space. Okay, and what linear dependence is thinking about is how do these, what is the space of all possible z's I can get, right? That I can get by some sort of operation like this. Okay, linear independence is trying to kind of, what we'll discuss is how to think about and quantify like sorts of things. And so this is be a little bit harder to draw in the plane in 2 dimensions. The concepts are kind of a little bit too simple in the plane to really grasp it. We'll try and draw some useful pictures later that give you some of the right intuition of what is going on here. But this is really important in thinking about much higher dimensions. Okay, so if I have this set of vectors, so if I think of this set of vectors x, right? This is my x1 up to xk, right? Then this, think about all the z's I can get. This is known as the span of x, right? Of the set x here is the set of all the values of z, right? So such that, so this is such that the following is true. I can write z as the sum of I equals 1 up to k, alpha I xi for some choice of these so these values of alpha. Okay, so the span of x is the set of all the z's I can get with these linear combinations of the vectors. Okay, and so if the span of x is equal to rd, right? So if I can recover all the vectors, any vector in rd, then the set x is known as a basis. Okay, it's a basis. It means that I can use those vectors x to describe any vector in rd, right? So if I want to know if I have a kind of some sort of algorithm that's trying to find the best point z, and I have a set of x vectors, and I'm choosing the values alpha, and I'm trying to find the best z, well, I know I can get any point if it's a basis, if the span is equal to all of RD. And so we'll talk about conditions under which this is going to be true. Okay, yeah.
That's a basis of RD.
A basis of RD, yeah. Typically, the of RD is implied in that the vectors here were already in RD, so that's the space that we're talking about here. Yeah. All right. Well, let me just say let's go through some examples of this. So let's say that x equals x1, x2, and I have x1 is equal to 1, 3, 4. Okay, and x2 is equal to 2, 4, 1. Okay, so these are vectors in R3. Okay, and so I can recover, for instance, I can get a vector Z1. So call this Z1. If I do, say, 1 times x1 minus 2 times x2, right? So in this case, alpha 1 is equal to 1, and alpha 2 is equal to, so minus 2, right? And so now I can write this out as 1, 3, 4 minus 2 times 2, 4, 1, right? And the negative 2 goes, it's a element-wise operation, and then I add them element-wise. So I'm going to get minus 3. 3 minus 8 is going to be minus 5, and 4 minus 2 is going to be 2. Okay, so this would be a vector Z1, which I can get in the span of x1 and x2. Okay, so I say, okay, but there are other vectors that I can't so necessarily get, right? In this case, so is there a way to write Z2 equals 3, 7, 1 as equal to alpha 1 x2 plus alpha 2, x1 here, alpha 1 times x1, alpha 2 times x2, right? So can I find, am I able to find choices of alpha 1 and alpha 2 so that I can recover this value, this vector 3, so 7, 1? Well, it seems like doing alpha 1 and alpha 2 both equal to 1 would start to be a good choice, right? If I set this equal to 1 and this equal to 1, then I'm going to get, well, 1 plus 2 is going to be 3. 3 plus 4, right, is going to be 7. So I got the first two correct, but the last one is wrong, right? This last one, 5, here is wrong. And so, so this is a problem, right? So this is kind of, this is not equal to, so Z2. And in fact, there's no way to choose alpha 1 and alpha 2 so I can get this vector, so Z2. Okay. If we went back, we talked about on Thursday this linear equations where there are some knowns and unknowns, and I'm trying to solve for these. If I did some algebra to try and solve for alpha 1 and alpha 2 to make this expression true, there's no solution here. There are in fact 3 equations I want to satisfy and only 2 unknowns. And in most cases, I can't actually kind of satisfy that equation, right? So there's actually a 2-dimensional space of vectors I can get in a 3-dimensional world. So most vectors I can't get, and only some vectors I so can get, right? This Z1 is known as a so linearly dependent, and this Z2 is so linearly independent of X, right? So this would be usually so linearly dependent on X. Okay, so Z1 is linearly dependent on X because I can write it as a linear combination of the vectors in X. And Z2 is linearly independent of X because I can't write it as a linear combination. Okay. Okay, so this is kind of an example. Let me kind of state the definition so more specifically. if I have a set of vectors x, x1 up to xn, I'd say these vectors are going to be so I'm going to say another vector, and these are this is a subset of Rd. Another vector in Rd is linearly independent of x if there does not exist alpha 1 up to alpha, let me use k here, alpha k, so I can write z equals the sum j equals 1 to k of alpha j xj, right? So if I there does not exist. That's what that symbol means. Backwards e with a line through it. Probably should just write there does not exist these alpha 1 through alpha k, so that I can write it as this linear combination. Okay, that would make z linearly independent of the set x. Okay, and then if I can, so otherwise, we say that z is linearly dependent. So okay, that means that there does exist some alpha. Okay. The other definition is I can talk about whether the set X itself is so linearly independent. So I say X, the set X is so linearly independent if for each xj in the set X, I so there is no alpha 1 up to alpha j minus 1, alpha j plus 1 up to alpha k. So xj is equal to the sum of I equals 1 up to k for I not equal to j of alpha I xi, right? So the set I say is linearly independent if there's for every vector in the set, I can pull that out and I can't write it as a linear combination of like the other elements. Okay, so if I had in the previous example, if I had x1, x2, and xj together in a set, right? If I had x1, x2, and z1 together, so now I'm going to have that. If I have a set x1, x2, and z1, is the set going to be linearly dependent, or so is it going to be so linearly independent? This is so linearly. Right, I can write z1. I could pull z1 out and write it as a linear combination of these two. So this would be dependent. Okay, whereas in contrast, if I consider a set x1, x2, z2, right? Remember these, I said these vectors were so linearly independent, then this set is going to be linearly dependent. Okay, so I can talk about sets that way. And what I would like is a set of vectors that each is adding something. Each vector is telling me something independent of the other ones. I don't want to be dependent on all the other vectors. Then it's not useful to add that vector to the set. Yeah.
So are you looking at G1, G2 relation of X1, X2, not relation?
It'd be the same with the other way. I could also pull out X1 here, and I could solve for, no, in this case, in the first set, right? I could pull out X1 and I could write that as a linear combination of X2 and Z1. And I could do this with, some algebra, right? What I would do is to pull out X1, well, I would say Z1 plus 2 times X2 should equal to 1 times X1. And if it was something else times X1, then I divide, that one coefficient, I could divide that through on the left-hand side as well, right? So I could, if they are linearly dependent, I could pull out any of the vectors and recover it with the ones that remain. Yeah, through basic algebra, right? Linear algebra allows us to do all sorts of algebra you learned in maybe high school or something on space of vectors, and then you could do the same thing on matrices, although we don't need to do that on matrices in this course. Okay. Okay. Let's all right, how about we take a 5-minute break until 11:45, and then in the last 20 minutes, we'll talk about rank, and I'll do some stuff on Colab in Python. I'll show you how to do this. So, yeah, 5-minute break sounds good? Okay.
Yeah, I don't.
Student asked me he wants to practice with quiz using the examples in the textbook.
Okay.
And he was wondering how to get feedback since he doesn't know where, like, there's an answer somewhere.
Yeah, we don't have an answer sheet, so you can post on Canvas or email the TAs, but I don't publicly post it so people can reuse the questions.
Right. Okay. Well, I was thinking I'd say something, send us your.
Yeah, you can email the TAs and we're happy to give or even post them on Canvas. So I was working through this and I got stuck. Yeah. And the textbook questions are typically harder than the quiz questions.
Yeah.
Although there are some things which should be reasonable for the class.
Yeah, they were asking about any other resources, and I was thinking I would just say some of the help hours, and we can find out what you need to practice, and then we'll give you practice questions.
No matter how much I give them, they always want slightly more, right? Got a whole textbook outline and notes and videos and help hours, and there's always asking for more. So I think hopefully it's a reasonable amount.
Yeah, it's anxiety.
Yeah, I understand. Yeah.
I also am going to say to check to review your examples in the lecture, essentially. At least I noticed in the class.
Yep. Yeah.
Basically the lecture.
Right. Yeah. If I do the lectures correctly, then what is covered in them will be kind of correspond with what's the most important, which will be what is valuable.
Okay. I'll do that, and then if I get a lot of those questions, I was thinking I might just like post something on Canvas recommending students if they want practice questions.
Yeah.
Should I just emphasize help hours?
Yeah. No, I think it's fine. Just point them to the existing resources. There's a lot out there, and if that's not enough, we can create more example questions during all that.
And then you said the quiz is done, right? For the most part.
Bassam was double checking some things. He's going to send it to me by noon today,
Okay.
I think. So,
But if, do you think
but
I
it should be,
can do
it should be pretty much, it should be pretty much done. I'm gonna look it over after that and review it.
I think Anya wasn't sure about the I think we're working on that. I'll probably
Okay.
consider already, but
Okay, great, yeah, I can,
yeah.
okay, great. So let's get back to the lecture. So yeah, so welcome back everyone again, you know, from the bathroom or, so before we move on to the last, I just want to draw one more picture that I think might be helpful, but with some caveats to give some kind of picture of what it's kind of like to be vectors to be so like linearly dependent on each other. So let's give an example where I have, you know, I've got like a matrix. So I can think of, like, the reason I think about sets of vectors is because I might have a matrix, might be 3 vectors. I want to say is kind of I want to talk about the linear dependence of like the matrix, right? So this could be a matrix that is 0, 1.5, 2, 0.5, and 1, 1, right? So this is a 3x2 matrix. So the vectors are in 2 dimensions, which I can draw, right? So this is in 3x2. And so now I can draw these points if I do stuff carefully enough here. Okay, so let's try and draw these points. A1 is supposed to be 0, 1.5. So let's say that this is A1, 0, comma, 1.5. A2 supposed to be 2, 0.5. So let's say that is over here. A2, sorry, 2, comma, 0.5, right? And then A3 is 1, 1. A3 equals 1, 1, okay? So these 3 vectors are going to be linearly dependent on each other, right? And one way of seeing that is that I can hopefully draw a line through all 3 of these. Okay, so there's a line that goes through all 3 of these vectors. And so I can kind of draw, there's like this space, this linear space, that's a kind of, I can get from one vector to the other. If they're linearly dependent on each other, there's a line or a higher dimensional subspace that goes through these vectors. Okay, so what's a little bit wrong about this? This is not the span, what I've drawn here. This is kind of the affine hull, technically, because I'm enforcing that this line captures so that the space of all vectors z alpha 1, a1 plus alpha 2, a2 plus alpha 3, a3. So alpha 1 plus alpha 2 plus alpha 3 are going to be equal to exactly 1. So it's this slightly other space. You often implicitly include the origin in the set as well. And so then I'm going to get the whole plane. I can get everything in this plane. So that picture is a little bit less sort of interesting. If I were to write kind of the things that are linearly dependent on one vector, right? The things linearly dependent on just one vector, say A1 here, or let's say pick A3, right? If I have A3, then I get to use the origin, and actually I can get anything on kind of this line that goes through here. So I get this linearly dependence on A3 is everything on this line. Linearly dependent on A3 and A2 is then the whole plane, right? So I'll already get the whole plane if I have A3 and A2 together here. So that's picture is less interesting, but in high dimensions, you kind of think about these linear subspaces you get based on the points and the origin. Yeah.
Can you also use for the columns A?
Yeah, the columns of A live in a three-dimensional space instead of in a two-dimensional space. So you can do it with the columns of A as well, but now I need to be thinking about a three-dimensional space and I can't draw it here. We will sometimes want to do that. When we do stuff like this, we'll try and walk through this slowly and sort of gradually, kind of introducing the ideas and definitions here, and then we'll use them and learn how to think about them kind of later on in the semester. But yeah, so you could do it with the columns as well. It's a different picture than this picture, because now there's two three-dimensional vectors, and I can't draw that picture very well. Okay. Okay, I want to do one more set of definitions. Is going to be the rank of a of a matrix. Okay, the rank of a matrix. Okay, so is going to be, or typically, or of a set of vectors. Okay, so we'll think about a matrix X, which will be an R n by D, but this is going to be equivalent to X as a set of these vectors, X1 up through Xn, and these will all be in Rd. So a set of n d-dimensional vectors. So I can think of the set of vectors, and the definition's a little bit so direct to write, because I might want to transpose this and think about the columns instead of the rows here. But if I think about a set of vectors, there's no kind of sort of like ambiguity. Okay, and it's going to be the rank is going to be the maximum number of so linearly dependent vectors in X. Okay, so it's the number of linearly independent vectors in X. The number of vectors I can pull out, and each one is linearly independent from the other ones I've pulled out before. Okay, and I can do this on the rows or the columns of a matrix, or on just a set of these vectors. So from our previous example, the rank of X1, X2, and Z1, this was equal to 2, because I could only pull out two of these, X1 and X2, but the rank of X1, X2, and Z2, this was going to be 3, because they're all going to be so linearly independent of each other. Okay? Okay, and so this kind of is telling you what this subspace picture, what the dimensionality of the subspace is. Okay, and so it turns out that if I think about the rows of A, then I can also think about the columns of A by writing A transpose, right? Think about the columns instead of the rows, or if I do the transpose, then the rows of A transpose are the same as the columns of A. Okay, and so it turns out that these two have the same rank. The rank is always the same. So the number I can pull out is always going to be the same. All right, and so we say that A is full rank if the rank of A is equal to the min of n and d. So the minimum of the number of rows and the number of columns. Remember, so it has to be the same. And in fact, we know that the rank of A, of a matrix A, which is n by D, is less than or equal to the min of n and nd. Okay, so if I think about if n is larger than d, so let's first think about the case where n is larger than d. We have more rows than we have, so columns, right? So so then we have these vectors living in this d-dimensional space. Can I have more than d linearly so independent rows? Or if I have d-dimensional vectors, can I have more than d linearly independent vectors? And so what this is saying is the answer is no, I can't. So the reason for that is every time I'm adding a linearly independent vector, I'm kind of increasing the subspace I can capture, right? So remember, one vector here gives me a one-dimensional subspace from the origin to A3. I can get anything along this green line. If I pick a second vector, I get that subspace as well, but also things that are some combination of these two, right? So if I get A2 also, okay, it corrected it and it showed I didn't draw it right. Okay, so great. So if I get A2 also, I get everything on this blue line through A2. I can capture that with the vector by scaling just the vector A2. And then if I have something in between, I can capture that. Like if I can get these two vectors by scaling them, and then I can take their average to get something in between, or something closer here depending on the weight. Or by making one of them negative, I can go off in this direction. And so I can capture anything in the plane now with two of them. So if I'm in a d-dimensional space and I have d vectors that are linearly independent, well, I can capture the whole space. And then I can't capture, I'm only in a d-dimensional space, right? So the rank, the number of linearly independent vectors cannot be more than d, right? And that's what this equation is saying here. And because they're the same, if I take the transpose, it means that if I do the transpose, I can't have it larger than the minimum of the two either. And so the reason, so if I want to think about that, let's say n is less than d. Okay, now we're still in a d-dimensional space, n is less than d. If I only have n vectors, so let's say we're in a 10-dimensional space and I have 3 vectors, I can't have more than 3 linearly independent vectors, right? Because I only have 3 vectors. Okay, so it can't be bigger than the minimum of either of these. Okay, and so if I reach the minimum, that's the highest the rank could go given the data I have. I say it's full rank. So we often want to work with matrices which are full rank. That means they're capturing everything going on. Okay, and we'll see how to think about this later in the course, in so a variety of places as well. Okay. So okay, great. Good timing. We have 7 minutes left. I want to show some stuff in Colab. Again, this is linked right here next to Numpy. This is a link to the Numpy library webpage that's a bunch of information about it. But I'm going to show you kind of basically all of the stuff you'll basically need to do, at least for now, in Numpy, and then we'll do some more complicated stuff with it later. But I just want to go through some examples and show you kind of how it works. It's a specific library, but it's easy to load in, right? So you import Numpy, we'll call it NP for short. So we're going to call functions of it, and we're going to refer to NP. And there's a linear algebra package within that we'll call LA for short. So we'll use some linear algebra operations, okay? So you need to import that. Okay, and then to create an array here, it's a bit clunky, right? MATLAB, I think, is better in this regard, but you say NP array and you put in the things in this square brackets, comma separated, and this is a vector, right? It's just an array, right? It's called array, but we'll think of it as a vector V, and it prints it out right, I can index into it, right? So if I index the second thing into the vector, it's going to be, right, you can see the answer already. It's answer is going to be 7. Okay. What does that mean? The indexes start counting at 0 or 1. 0. Okay. In MATLAB, they start counting at 1. So if you're used to MATLAB, you're probably used to programming with indexes starting at 0. Okay. Just if you're in computer science classes. Okay. If I want a 2x3 matrix, right? A matrix now, I make this as an array of, arrays. Basically, I call one NP array, but I put in it the square brackets, right? That's our comma separated sets of square brackets, right? And I get this A matrix, okay? I can now index into it by 1, 2, and this is, again, counting at 0. So it's the first row, starting at, the first is actually the second one. So not the 0th row, but the first row, and then the second, which is the third. So it's actually 7. It's the last entry there, right? And I can also, so this is a printing out the whole matrix. This is of the index into the 1, 2 entry. This is, I can do things like, okay, I want all of the rows. So I put a, so I'm putting this colon here, and then I can get all the rows starting at the 1th row, right? So which is the second one, and all the columns starting at the second one, and I get this submatrix. So you can call out these submatrices using this way. Okay. I don't think we need this. Here's another example of a matrix. This is a row and this is n rows and 2 columns instead. Okay. Okay, I can add vectors together. Remember, adding is element-wise adding, right? I had V before, now I have U. I can, gosh. Okay, okay, so I can print the vector V, right? So this was V 1, 2, 7, 5. U was 3, 4, 2, 2. Add them together, does the result, does it for you. You don't have to make mistakes like in class. V times U with that time symbol, that's element-wise multiplying, okay? This is typically not what you want to do. So if you use that star symbol, you're probably doing the wrong thing. It's going to be rare that you actually want to do that. Instead, you probably want to do, like the dot product of 2 vectors, right? There are multiple ways to do the dot product. Either I can call this dot operation, which takes 2 elements. I can do V dot of U, right? So I can string these together, or I can just use the at symbol. The at symbol is, the dot product. They all give the same answer here, okay? You can have, if I have 2 matrices, A and B now I can also do matrix multiply. And remember, matrix multiply is kind of, actually dot product was a special case of matrix multiply. Actually, the at symbol is the matrix multiply symbol. You can't just put them next to each other. It doesn't know how to deal with that. But again, you could call the dot product. These all give you the kind of the same answers here. You can do matrix vector multiplication as well in the same way. Okay, what is one thing a little bit weird is that, again, Python and Numpy does not like to think about transpose and is it a row or column vector. I should either not be able to do X is a 1x2 matrix here, and I do B, and B is 3x2. So it should only be able to multiply by 2x1 matrix. But it handles B multiplied by X fine, and it handles B multiplied by X transpose fine. It always transposes it into the way where the multiplication makes sense. It guesses you're doing the right thing. Sometimes you're going to make a mistake and it's still going to compute something. but sometimes you're gonna, and it's gonna compute the wrong thing. Most times it helps you out and it simplifies notation, so you don't have to write the transpose. Okay, let's quickly go through norms. You can calculate norms. The base norm, this is in the linear algebra package, with if the second entry in the norm function is the p-value, but if I don't specify it, it's a 2. Okay, so like I said, it's almost always the 2 norm. I can compute the 1 or the infinity norm of the vector, and I get different outputs here. And here's my matrix A. Must have been a slightly different than what was in the book, but here's A, 3, 4, 3. Okay, so this is slightly different than the example I wrote before. This is where I got the 1095 from. So the Frobenius norm is slightly larger than the spectral norm, right? I need to write this weird single quote FRO single quote to get the Frobenius norm. Okay, and one more thing I want to show, maybe we'll go over this again on Tuesday, but it always prints a vector as the row vector. This can be a little confusing. A and A transpose, I print them out, it prints them differently, but the vector transpose, it always prints out the row vector. So I do X, print X transpose, and X, it always prints out the row vector. So keep that in mind, that it's really not storing, or it's not caring about the transpose as much as it can. Okay, great. We'll stop there. Quiz is on Thursday, so don't forget your cheat sheet, and hopefully you'll take it in class. We'll be able to answer questions here.